we are now going to formulate the mean variance portfolio optimization problem in the style of Markowitz. So what Markowitz did, he considered that once you make an allocation W, the risk associated with W is the variance, which we had computed yesterday, where W is the allocation, this is the variance covariance matrix. And the reward that is associated with the choice of omega, which we will symbolize as rho x, which we will call reward. And this is what you expected to get, this is the expected return, nothing else. Is summation Wi Ri bar. And often for the sake of convenience, rho W is also written as R bar. So for the sake of convenience, we will write R hat, this vector, as R1 bar or n bar. Instead of writing column vector, I am writing it as a transpose. The vector is always meant to be a column vector. Now so I know what is the risk and I know what is the reward. So there must be a trade-off between the risk and reward. You cannot have a lot of rewards without any risk. Now before I proceed further, I need to make a comment. The comment is that I am using terms like variance covariance matrix, and this is what I expect the students to know. In the sense that if the students expect that every little thing about statistics that we use here, basic statistical tools, has to be explained, then this course cannot be completed. This is a course for finance, and hence people have to come knowing these basic things. Whatever details or extra things that was required, that was done in the first part of the course to study quantitative finance or mathematical finance. But it's important that if you feel uncomfortable by such terms, you need to go back and look into some books or some lectures on the web. So we are not going to go and to keep on explaining how this comes and why this comes and all these things. Okay, so this is sigma. So don't confuse it with the sum notation. Now once this is done, how do we formulate our model of one is in terms of the utility, or rather we define the utility as a trade-off between the reward and the risk. So we write the utility, my utility when I choose W, some sort of this is a trade-off function with some parameter mu, so this is something which I want. I want that this difference should be as large as possible. So what I want to do, I essentially want to maximize this utility function subject to the fact that these vectors are equal to 1. Now here you might ask me the question, are these not all summing up to 1? So are these not all non-negative? The answer surprisingly is that it might not be non-negative always, because here we keep in the idea of short selling. Short selling means that you are trading in an asset which you don't own. So short selling very simply means trading in an asset you don't own. Suppose what you do, you take one asset from a broker. So you take an asset from a broker, say the asset number 2 you have taken from the broker. What you did, you sell it in the market at whatever be the price, right? So you sell at time t equal to 0 with some price, and then at time t equal to 1 you buy back that asset, say asset number 2, and you return it to the main guy. So that is essentially the job. So here positive weightage means when you are making an investment in the market, we give positive weightage. So you have some money, and if you are making an initial investment, that is viewed as a positive investment. If you are getting some money, that is thought of as a negative investment. You are getting money, you are not investing. So here it could be plus 1 on anything. So you could be doing short selling. So if I do not want to have short selling, so this is a standard model. So this is with short selling. So we will also use other form. So here we are trying to maximize your utility, or the trade-off between the reward and the risk. So one can also have a multi-objective optimization viewpoint, which we will not discuss. Another is what would happen if you do not allow short selling. If you are not allowing short selling, then you of course have to know that you are making investments only, you are not getting money. So all this W1, W2, Wn has to be greater than 0. So your problem would now become subject to. So if you look at this, let us see what sort of a problem it is. Or here you could written minimization of the loss, which is the risk minus the reward. That also you could have done. Subject to summation Wi equal to 1, I equal to 1 to n, and Wi is greater than equal to 0 for all I equal to 1 to n. So there are two versions. Okay, we shall just use this version for our benefit, for simplicity actually. Now, is this the only logical model? See, this problem, if it has a minimum or a maximum, will have a global maximum, because this is a linear function of W, rho W, and this is a convex function of W. So it's linear plus minus of a convex function. So minus of a convex function is called a concave function. So f is concave if minus f is convex. So a concave function looks like this. If you take a function from R to R, that is, if you take any 2 points on the arc and join them, that portion, the part of the graph, the line segment would lie below the graph. So that's, and for convex it was above the graph. So this is a concave function. So linear function is both convex and concave, and this is a convex function, negative is a concave function. So when you maximize a concave function over a convex set, you have always a global maximizer. So this is one form of the utility, one form of the portfolio minimization problem, using variance as the risk and the expected return as the reward. Another important class of problem which we will now write down would ask us that, okay, I simply want to minimize my risk, but when, and I want to get those omegas, those W's, those allocations which will give me a certain level of expected return, that I want this expected return, and then once I get that sort of expected return among all the portfolios or among all the allocations which will give me this level of expected return, I would like to know which minimizes my variance. So that is what was really the Markowitz model, one form of the Markowitz model that we are now going to discuss. Okay, so now we will put in the second model. The second model is as in the following way. Now I have said that I only want those allocations which gives me a fixed return rho naught. Of course I know that my allocation should satisfy the weights basically. So once I know that I can get weights of this form, then among those weights I want to know which minimizes my risk, and that is exactly the allocation that I will make. So this is the one where you allow short selling, and this is, and if you do not allow short selling, then your problem would now look like subject to, here also I should write subject to, ST means subject to or such that, whatever you want to say. Rho of W is rho naught and summation Wi is equal to 1. Now let us, and of course Wi, this is with no short selling. First of all, you have to understand, as we have spoken about various types of optimization models in one of our class, these two problems are optimization problems with affine constraints. These are all affine, these are linear constraint, there is no additional part. So these are all affine constraints. So these problems are a quadratic programming problem QP with affine constraints. I would like to mention a result here which is usually known to optimizers, is that under this condition any KKT point is a global minimizer. So the standard technique of writing the KKT point is to construct what is called the Lagrangian. So suppose I take this one only, we can do it later on, that would be harder of course. So if I take this one, that affine constraints means that it's both equality and inequality, that is inequality plus equality. So I would now like to construct what is called the Lagrangian associated with my problem. So the Lagrangian means I would associate multipliers. This was Lagrangian multiplier rule is the one which you have learned in high school or your first year college in calculus. So only mathematicians working in optimization would do analysis to say that such multipliers would actually exist and such a condition would be true. So here I would have one constraint with this and another constraint with so I will have lambda 1 with this one and lambda 2 with the other one, and then I will write down the things in the following way, is that half of, so there is the way to write down the minus, if I look at this very carefully, it is nothing but this rho w is nothing but r hat omega minus rho naught minus lambda 2. This can be written as EW minus 1. So what is E here? E here is the vector. So basically I am taking the inner product with the vector W. W is here W1, W2, Wn. So that I am not writing. I am sure that everybody understands this basic fact. So what essentially is the set of Karush-Kuntakar conditions in this here is, first take a, so the KKT has the following form. So first take a gradient with respect to L and equate it to 0, and then then of course you need to satisfy these constraints. That is, you first take with the lambda 1 and then take with lambda 2. So you have to satisfy the constraints. That's it. So this is the KKT system that you really need to solve. Note that if I have uncorrelated assets, then this variance covariance matrix becomes a diagonal matrix consisting only of variance. So let me take an example now from Leuenberger investment science. So my source of the example is Leuenberger investment science. So the example consists of 3 uncorrelated asset. So yes, n equal to 3 assets are uncorrelated. N equal to 3 and assets are uncorrelated, and let their means, so each has variance 1, so sigma 1, so sigma 1 square is 1, sigma 2 square is 2, sigma 3 square is 1, 1, and their R1 vector is 1, or 2 mean is 1, or 3 body is 1. So this data is given to me, right? Now I want to find what is my optimal W. That's essentially what it is. That's my job. So now we are going to write down this condition. See, we are going to now write down this condition, the KKT. So you are taking the grad with respect to omega. So what do I get? I get here half as the first condition, sigma W minus lambda 1 r hat minus lambda 2 E, and that's equal to 0. Of course, first let me clarify this. So let me write, sorry, this is half is gone because had I put half, if I, yeah, half was there. So that in the derivative half was gone. So now this is nothing but sigma 1 square, sigma 2 square, omega 1, omega 2, omega 3. So here is a vector sigma 1 square omega w1, sigma 2 square w2. See, even if I say omega in place of w, it is w. So I make this slip, so forgive me for this. It's very difficult to correct it suddenly unless I become conscious. Maybe I should have started telling omega only, but it doesn't matter. Now this is R1 bar, R2 bar, R3 bar, and this is 1, 1, 1, and this is equal to the 3-dimensional 0 vector. So once you have, now we would like to write them down in terms of equations. Sigma 1 square, this, minus lambda 1 R1 bar minus lambda 2 is equal to 0. Okay, this is exactly but sigma 1, sigma 2, these are all 1 already given to you, so I can just remove this part. So this is all 1 which is already given. But what is R2 bar? Sorry, here I have made a mistake. R2 bar is given as 1, 2, the data is given as 1, 2 and 3. So R1 bar is 1, R2 bar is 2. 2 lambda 1 minus lambda 2 is equal to 0. And then I have omega 3 minus 3 lambda 1 minus lambda 2 is equal to 0. These are the three equations. Sorry, this data I had made a mistake. The data was 1, 2 and 3. So this is an example which is worked out there, but I am giving a step-by-step explanation. So the omega that I found out here will satisfy the Karush-Kuhn-Tucker condition that I will find out here. Once it satisfies the Karush-Kuhn-Tucker condition, I am completely sure then that this is my omega which I want to do the allocation. This is my solution. Obviously now you will have another equation which is the second equation. So omega 1, 2W2, 3W3 is equal to your expected level, which is rho naught. And then you have W1, W2 plus W3 is equal to 1. So how will you solve it? Find out W1 from here, W2 from this equation, W3 from this equation, and put it here. So once you do that, you will get two equations. 14 lambda 1 plus lambda 2 is equal to your rho naught, and 6 lambda 1 plus 3 lambda 2 would be equal to 1. So what are you doing? Your W1 is nothing but lambda 1 plus lambda 2. You put it lambda 1 plus lambda 2. W2 is 2 lambda 1 plus lambda 2. W3 is 3 lambda 1. So just put it there and add and see. This is exactly what you will get. Because here you will have a lambda 2. Sorry, that cannot be like this. It has to be lambda 1. So lambda 2 is here, 3 to 6. So there must be 6. Because 3 lambda, there should be 3 lambda 2, 2 lambda 2 and 1 lambda 2, 6 lambda 2. So this should be the equation. In the next case, obviously you will have lambda 1, lambda 2, lambda 2 will come 3 times and this will come 6 times. naturally. So okay, so these are the equations. So once this equation is done, then I can find out what is lambda and what is, let's say, lambda 1 and lambda 2, and that is exactly what I want to now write down. So here I have lambda 1 which is equal to so everything will come in terms of rho naught, the parameter, your expected return that you really want. This will be your lambda 1 and your lambda 2 would be 2/3 minus rho naught. So once you have this, put in the lambda 1 and lambda 2 here, and that will immediately give you your omega 1, omega 2 and omega 3. So, or W1, W2 and W3. So I leave these things to your homework, maybe just W1 and W2. W1 is lambda 1 plus lambda 2, which would be lambda 1 plus lambda 2. So it should become rho 0 2 rho 0 2 minus 1 plus 2/3 minus rho 0. Wait, okay. You see, this is what's coming. So 4/3, I think, so sorry, there was a small mistake in my calculation because I am standing and doing the calculation. I think lambda 1 is alright. Lambda 2 is not 2/3, it's 7/3, sorry. 7/3 minus rho naught. So then your omega 1 is now lambda 1 plus lambda 2. So lambda 1 plus lambda 2 means this will give me 4/3. So this minus this 4/3, and this is minus rho naught by 2. Similarly, I leave you to find out the rest as a homework. So this is a very simple situation, uncorrelated situation. What about the general situation? In our next lecture, we are going to talk about the general situation, and so this portfolio optimization would essentially now consist of 4 lectures, and the last one we are going to look in more detail about the interaction between the risk and the reward, and then we will talk about the capital asset pricing model. Okay, so see you in the next class.